right, welcome ladies and gentlemen. This is the really brief Redox basics video, just meant to get you sort of caught back up to the level of redox understanding that we're going to need for our discussion of electrochemistry. None of this information is new. All of it is review. It's all sort of fundamental oxidation reduction chemistry. You can also read in the book about this, but it's just kind of a reminder of some of the basics about redox chemistry. First of all, the definitions. Oxidation, hopefully remember that definition. That is the loss of electrons in a chemical process, and reduction is the gain of electrons in a chemical process. At first glance, these terms might appear to be slightly confusing because we think reduction, that means getting smaller, so why is it the gain of electrons? But recall that that means that it's the oxidation number that's being reduced. So the charge on the species is getting lower because it's gaining electrons. So that's why we call it reduction, because the gain of electrons causes a reduction in charge. And remember that the way that we have to remember this, we've got a couple different mnemonics, but the one that I like is Leo the lion says grr. Remember that Leo the lion says grr. What does Leo say? He says grr. Because LEO, that's loss of electrons, oxidation. GER, gain of electrons, that's reduction. So that's how we remember those terms. And I still say that to myself when I'm looking at a redox problem. I'm like, okay, which is which? Okay, Leo, loss of electrons, oxidation. GER, gain of electrons, reduction. So I still totally use that, even though I've been studying chemistry for over half my life. With redox reactions, the big thing that we're going to talk about in this unit, we are not so focused on the basics of redox, on like what oxidation is and what reduction is, because we already know that, but we're going to be talking instead about electrochemistry. It's called electrochemistry for a reason, and what we need to realize is that these redox reactions, this oxidation and reduction together, they result in an electric current, because you look at these definitions of oxidation and reduction, you realize that electrons are moving around. They're changing locations. They're being lost by one thing and gained by something else. That means that the electrons are moving. They're changing places. And that movement of electrons results in an electric current. And that's where we get the term electrochemistry from, where electrochemistry is essentially looking at, what happens when we have this chemical process that results in a current, or that needs a current, or that somehow involves the movement of electrons from one place to another place. So, electrochemical process. You are undoubtedly going to be seeing this phrase a lot in questions relating to this unit, electrochemical process, and it means, it's a very blanket term. It can mean one of two things. It essentially refers to anything at all where electrons are moving from one location to another. It could mean either a spontaneous reaction or a non-spontaneous reaction. So it could mean, in this case of this first example, redox reaction. It always means redox. No matter what, it's always going to mean redox. But it could mean this first one right here. The energy released by spontaneous reaction is converted to electricity. So basically we have this spontaneous process that has a chemical process that's involved that will generate an electric current. So we are converting to electricity. This would be, for example, a battery. Something that can spontaneously generate electricity on its own. It's a chemical process. It is absolutely a chemical process, and we get an electric current out of it. That's why we use batteries on the go, because they don't need to be plugged into anything, because they're simply spontaneously doing this redox reaction that is capable of generating an electric current that we then use to power our various devices. Or it could mean that we are using electricity to cause a non-spontaneous reaction to happen. So instead of generating electricity, maybe we need to use electric current, use the movement of electrons to force something else to happen. That's actually where the battery powering the cell phone is a good example. The battery in and of itself is a spontaneous process, but the powering of the cell phone is not. Your cell phone does not do what you would like it to do without the battery in it. But you put the battery in it, and then the battery forces the cell phone to do something, and that is also an example of an electrochemical process. So it could be either generating electrical energy or using electrical energy, but we still see that that electrical energy has to be there because that's based on the movement of electrons, and that's redox. That's what redox is, electrons moving around from place to place. So if we just look at an example reaction, just as a bit of a reminder about some oxidation numbers, we have this reaction right here, 2 Mg solid plus O2 gas goes to 2 MgO solid. This is an example of a redox reaction. And if we consider magnesium and oxygen separately, and we're looking simply at oxidation numbers, we see that the magnesium in this reaction goes from oxidation number of 0 to begin with, to an oxidation number of +2 when it's in MgO. That's thinking about charge, right? That's thinking about the magnesium on its own has an oxidation number of 0, but when it's in that compound, it's got an oxidation number of +2. We see that the magnesium is losing electrons, right? It starts at 0, it goes to +2, and that indicates a loss of electrons. Now the 4 electrons, you might be saying, but Mrs. Julian, that's 2 electrons that's changing. It's going from a charge of 0 to a charge of +2, so it only lost 2 electrons. Well, we've got 4 electrons here because based on the coefficients in the chemical reaction up here, I've got 2 Mg's goes to 2 Mg plus 2's, so I'm carrying that over. So this is sort of saying like 2 times 0, 2 times +2. That's why I'm going to need the 4 electrons right there. And then we also have in this chemical reaction oxygen. And the oxygen starts at an oxidation number of 0, and then it winds up as -2. Just knowing what we do about charges, remember, review oxidation numbers if you haven't already. That's a reduction. This is showing a reduction, a gain of electrons. In order for that oxygen to go from 0 to the -2, it has to gain electrons. We are reducing the charge. We're going from 0 to -2. And again, we're adding 4 electrons here because we've got the subscript. It's O2, and then we're creating 2 oxygens with each with a -2 charge. So 2 times -2, we have to have 4 electrons involved to get it to go from the 0 to having a sort of net total charge of -4. Conservation of charge, this is going to be a big thing for us when we're looking at our redox reactions. Electrons are not lost in a chemical reaction. What I mean by that is when you have the half reactions, which we're going to be talking about, you've got to ensure that you've got the same number of total electrons involved. That is, the number of electrons that you have written on the left in one of your half reactions has got to be the same as the number of electrons on the right. Conservation of charge. Electrons are not lost. They are conserved. If one thing loses 6 electrons, something else gains 6 electrons. If one thing loses 14 electrons, something else gains 14 electrons. So the number of electrons has to be the same. You can't have a chemical process where the thing that's being oxidized is losing 2 electrons and the thing that's being reduced is gaining 25. Where are those additional electrons coming from? They have to be conserved. The numbers have to be the same. So half reactions, we're going to be seeing this a lot. They simply they're not a balanced chemical equation. They're not an overall chemical equation, but they will show overall conservation of charge. Total net charge on each side will be the same, but they're meant to separate out the oxidation from the reduction. Now, obviously, oxidation and reduction have to occur together, but we can show the processes separately, and that's what the half reaction is. In a half reaction, as we saw in that previous example with the magnesium and the oxygen, it shows electrons as reactants or as products. Now, I very much, and the AP as well, I only like to add electrons. So electrons are only ever going to be added, not subtracted from one side or another. So for example, if we take this total reaction right here, so this is an overall balanced equation. We've got tin plus 2 iron 3s goes to tin 4 plus 2 iron 2s. First of all, conservation of charge, real quick before we separate it out into the half reactions. we get a total of a +2 charge from the tin on the left, and then 2 times +3, we get a total of +6 from the 2 iron 3s on the left. So all together, add these things up, we get a total of a +8 charge. And then on the right side, we've got +4 from the tin, and then 2 times +2, that's +4 as well. So total on the right, we've got a +8 charge. That's conservation of charge. That's showing that the number of electrons that are being exchanged here between the tin and the iron are the same number, that we're starting at the same charge that we're ending. Because the only way we wind up with the same charge on each side is if the electrons involved match up. But looking at this in terms of half reactions, what's oxidized, what's reduced? Well, the tin starts at +2 and goes to +4. The iron starts at +3 and goes to +2. So for oxidation, where electrons are being lost, it's and reduction versus electrons being gained, the tin is losing electrons because that's how it's going from that +2 to the +4 charge. It has to lose 2 electrons. So in order to indicate that electrons are being lost, electrons are products. Just like when heat is lost, that's exothermic, and heat is a product, it's the exact same idea here. If electrons are being lost, they have to be a product, meaning that tin +2, it started with a certain number of electrons, and then it wound up with 2 less electrons. That's how it went from tin 2 to tin 4. It lost 2 electrons. So it started kind of with all of its original ones, and then those 2 electrons that we're showing as the product, they're no longer a part of the tin. They are separate from the tin. The tin has lost those. They are no longer associated with that atom. Realistically, they're moving through the wire in order so that they can join up with the iron. And then the iron half reaction is going to be a reduction half reaction. The iron is going from a +3 to a +2 charge. That is a reduction charge. The only way that we can get the iron to go from +3 to +2 is by a gain of electrons. Now notice I am keeping the coefficients intact at this point. So I'm keeping it as 2 Fe+3s and 2 Fe+2s, which means that instead of simply having 1 electron being gained, I am showing 2 electrons being gained in order to ensure that the total charge on each side of this half reaction is identical. But the point that I want to make here again is that when we're talking about reduction, electrons are reactants because they're being gained. Again, think about an endothermic process. In an endothermic process, heat is gained, heat is absorbed. Heat is a reactant. That heat has to enter the system. It didn't start in the system, it's coming into the system from the outside. Reduction is very, very similar. Electrons are reactants in a reduction half reaction because they have to enter into the system. That iron 3 is not starting with all of the electrons that it winds up with. So we have to gain those 2 electrons from the outside. So that's our redox. Real quick review of some of the basics of redox chemistry, getting you caught back up to speed. And then the next video is going to be about balancing balancing redox reactions in acids or bases.